sequence A so that the pivot element would be in its correct position, and everything to the left would be smaller than or equal to pivot, and everything to the right would be greater than pivot. Once this is done, then we can recursively sort, or we can recursively call the quicksort algorithm to sort the left part of the array to the left of the pivot element, and recursively sort the right part of the array. If we do this, then we get the whole array A into sorted order. We analyzed the running time of the quicksort algorithm. We did two types of analysis. One of them was the best case and one of them was the worst case. Let's quickly review those analyses. So we need to, since the quicksort algorithm is recursive by nature, we need to write down a recurrence that represents the running time Tn of quicksort. So to do that, we said we can define T of n representing the running time of quicksort as follows. Since we drew a partition, we don't know where the pivot element will end up. So let's assume that pivot element ends up at this position I, at this index I. This means that there will be I elements to the left of it, and there will be almost n minus I elements to the right of it. So this means that the first recursive call will work on I elements of the array, and its running time will be T of I, plus the second recursive call will work on n minus I elements. It means that its running time then will be T of n minus I, plus we have seen that the running time of the partition function itself is theta n, is n. Okay, so we wrote down this recurrence to represent the running time of the quicksort algorithm in general. Depending on where the pivot element ends up at index I, we can solve this recurrence in different forms. So for the best case happens when the pivot element ends up almost in the middle of the array. So for the best case, I, the index where the pivot element ends up, will be almost in the middle of the array, which means that this will be T of n divided by 2, this will be T of n divided by 2, so we will have 2 times T of n divided by 2 plus theta of n. And in our previous lectures, we had seen that if we have this recurrence, running time T of n is theta of n log n. This is the best case analysis of the running time of the quicksort algorithm. For the worst case analysis, the pivot element ends up either at the left end of the sequence or at the right end of the sequence, so that the partition algorithm actually ends up with a quite unbalanced sequence. So in the extreme case, it will be the case that the pivot elements might be the smallest element so that it ends up at the leftmost index, or in the other case, it might end up in the right end as well. So in either case, if the pivot ends up to the left of the array or ends up to the right of the array, in either case, we will have the following. So one of the recursive quicksort calls will only work on a single element. So this will be constant time. But the other one, the second recursive call, does anybody have a similar problem with Emir? Can everybody see the screen that I'm sharing? So does anybody have any problems viewing the lecture? Okay, if it is fine now, then we can continue. For the worst case, we said that we will have it due to the internet connection problem. So if it is fine now, we can continue. So for the worst case, the partition algorithm will end up with an unbalanced partitioning so that one of the recursive quicksort calls, say for instance, if the pivot is the leftmost element, this first recursive call will almost do no work and it will end up with constant running time. But most of the work will be done with this second quicksort call, which will have to work on n-1 elements. Okay, so in the worst case, we will have the second recursive call will have to work on n-1 elements, which means that it will spend t of n-1 running time and plus again theta n for the time that we spend in the partition. Okay. Note that even if the pivot is the largest element, which means that pivot ends up in the right index, in this case now the first quicksort recursive call will spend t of -1 time and the second recursive quicksort call will spend constant time. In either case, this will be our recurrence for the worst case, t of n-1 plus theta of n. And in our previous classes again, we have seen that this recurrence evaluates to t of n is equal to theta of n squared. Okay, so for the worst case, the running time of quicksort is theta n log n, which if you remember is actually the running time that we have found for merge sort and the heap sort algorithms. Let me turn off the camera so that maybe there won't be any freezing problems due to the internet speed. And for the worst case, the running time of quicksort is n squared, which if you remember is actually the same as the worst case of the insertion sort algorithm. Now for the quicksort, we will introduce yet another type of analysis, which we will call average case running time. Okay. Note that this was the general recurrence that we have written no matter where the pivot ends up, because I is a parameter and we have parameterized our recurrence relation based on the position of the pivot element. Okay. Now to do the average case running time, we will consider a very small modification to the main algorithm. The small modification consists of the following. Before doing our partition, before calling our partition, we will do the following. Remember that before the partition algorithm assumes that the leftmost position at A left is the pivot element. Okay, and then it's basically swaps the elements of the array in such a fashion that this pivot element at A left ends up at its correct position. Everything to the left is smaller than or equal to, everything to the right is greater. What we will do as a small change is that we will pick among all the elements in between the indices left and right, we will pick a random element. Let's say the random element that we have picked, a random index. We will swap the position of A left and this random index. So this random index element will now be at the leftmost position. This is all the change that we will do to our algorithm. Okay, so we can actually show this on the pseudocode as well. Let's view the pseudocode for the partition algorithm. Right in here, right before we start our partition, we will swap. So we will do a swap A left, basically the leftmost element, with a random element in the array, with So with, let's say, a index. This is all the change that we will do to our main quicksort algorithm. The only change will happen at the beginning of the partition, where we will swap a random array element with the element at the leftmost position. The rest will be the same. Remember, for the rest, the partition algorithm assumes that pivot is at the leftmost position. What do we gain by doing this small change? With this small change, we guarantee that our pivot element is basically a random array element. So it can be at any index. Okay, this is the guarantee that we will have with this small change. Although this change might seem not very important, we will see that with this small change, we will be able to do an average case analysis of our quicksort algorithm. Let's get back to now our average case analysis, assuming that we have done this small change. Note that even if we do the small change, we may still have a worst case running time of n squared. However, we will see that with this small change, the expected running time of the quicksort algorithm, or the average case running time. So we can use both notations. We can both of them mean the same thing, expected running time or the average case running time. We will see that average case running time will not be as much as this. Formally, remember, this was our recurrence. So we do the partition and our pivot element ends up at index I, and we have I many elements to the left and minus I many elements to the right. So we spend T of I minus 1 running time to sort the left part of the array, T of n minus I running time to sort the right part of the array, and plus n running time for the running time that we spend for the partition algorithm. Okay. Now, to continue with this is where the random choice for I comes into play. Okay. Since we have chosen our pivot element randomly, what we can do is we can write this sum T of I minus 1 and T of n minus I over all possible values for I. So it could be the case that the pivot index, the pivot element, is the smallest element, so that I is equal to 1. Or it could be the case that the pivot element is the second smallest element, so that I is equal to 2. And we can continue in this way. I can be 3, I can be 4, all the way up to n. Since we have chosen this our pivot value randomly among all the elements of the array, each I in here in between 1 and n is equally likely to appear. Which means that we can sum all of them to find out this sum Ti minus 1 plus Tn minus I. We can sum this value for all possible values of I and take the average by dividing the sum with n. Okay. Now this becomes our new recurrence. If we do some math, we will see that, so we are just adding up. We divide this summation into two sums, summation of T of I minus 1 from 1 to n. Same is here, summation of T of n minus I from I equals 1 to n. These two values are actually equal, these two sums, because the sum is actually T of 1, T of 2, T of 3, T of all the way up to T of n. This is the same from the opposite order, T of n plus T of n minus 1 plus T of n minus 2 all the way up to T of 1. So both of them are the same. we can represent with a single sum multiplied with 2. And if we do some math, I won't show the details of the math. So this is the recurrence we end up, and if we do some math work on this recurrence, at the end we will see that T of n will be upper bounded by n log n. T of n will be big O of n log n. So this was, you can actually later on check out the details for the math required in here, but just to give you an intuition. So note that the best case running time is n log n. The worst case running time is n squared. The analysis that we have just done tells us that the expected running time of the randomized quicksort, note that with that small change, we can call our quicksort algorithm randomized quicksort algorithm because we are picking our pivot value randomly. So that tells us that the running time of the randomized quicksort algorithm on average will be the same as the best case running time of the quicksort algorithm. Just to give you an intuition of this, rather than providing these mathematical details, consider the following. So consider the case where note that we said that the running time of the quicksort algorithm will actually depend on where this division happens, where our pivot value ends up. Okay. For the best case, we said that the division happens so that we have a balanced division, almost n divided by 2 elements are to the left, almost n divided by 2 elements are to the right. The bad case for quicksort happens when there is an unbalanced division where, let's say, a constant number of elements are left to the left of the pivot, whereas almost n many elements are left to the right. Now let's consider a version of a bad case, a bad input case being given to the quicksort algorithm. Let's assume that our partition is quite bad, so that let's say the pivot element is quite to the left of the array, such that to the left of it, if there were n many elements in the original array, let's say that only 1/10 of all the elements are to the left, and the rest of the elements, the big chunk, consists of 90% of all the elements. So that we have 9n divided by 10 elements to the right. So this instance, such a division, such a partition, could actually be considered a bad partition because it's quite unbalanced. 90% of all the elements are on the one side of the pivot and only 10% is on the other side, which means that one of the recursive calls to the quicksort will work on a small piece, whereas the second recursive call will work on a big chunk. So this is actually quite a bad partitioning instance for the quicksort algorithm. Okay, so this is something close to a bad case for the quicksort algorithm. But we will see that even if this bad partitioning happens, the running time of the quicksort algorithm will still be not as bad as the worst case running time, which is n squared. Even if this bad partitioning happens, it will be as good as the best case, which is theta n log n. Let's see how that happens. Let's try to write down a recurrence describing this case, describing such a situation. So we will, as before, we describe our recurrence with T of n. So one of the recursive calls for the quicksort algorithm will work on an input of size n divided by 10, which means that the time spent for that recursive call will be t of n divided by 10. The second recursive call to the quicksort algorithm will work on an input of size 9n divided by 10, which means that the time spent for the second recursive call will be t of 9n divided by 10, plus the running time that we spent to do the partition, n. Now, such a recurrence assumes that this bad partitioning happens in all the recursive calls as well. So when quicksort works on this big chunk, the partition algorithm again divides the input instance unevenly in an unbalanced way, so that only 10% is here, 90% is to the right. Assume that this bad partitioning, which divides the input size to 90% and 10% in an unbalanced way, happens in all the recursive calls. This is quite a bad case. This should normally be quite a bad case for the quicksort algorithm. But let's try to solve this recurrence and see what it evaluates into in terms of our asymptotic bounds. Does anybody have a guess regarding a big O bound for this recurrence? Any guesses? If this is our recurrence, Tn equals Tn divided by 10 plus T of 9n divided by 10 plus n. Can anybody guess an upper bound, a big O bound for T of n, for this recurrence? Can everybody still follow the lecture? Can you all hear me fine and see the slides that I'm sharing? Any problems with following the lecture? Okay, any guesses regarding this T of n? If this is T of n, this recurrence, what is T of n in open form? Or can you give a big O bound for this, for the T of n? Or if somebody asks you, this is the recurrence and give me an upper bound, a big O bound for this recurrence, how would you approach the problem? What would you do to solve this T of n? For instance, we have actually, if you remember from our previous lectures, we have mainly seen two different methods to solve recurrences. One of them was constructing a recursion tree of the recurrence, and then trying to find a sum of all the values represented in the recursion tree. That would give us a guess regarding the given recurrence. This was one method, and then once we find the guess, we would all obviously formally prove that our guess is true using induction. This was one method. A second method was applying the master theorem, which was an easier method, but we could only apply the master theorem or use the master method in only certain special cases. In only certain special cases where the given recurrence T of n was in a specific format. Now, can we apply the master theorem to solve this recurrence? T of n equals T of n divided by 10 plus T of n 9n divided by 10 plus n. Any ideas? Does anybody remember the master theorem? So let's just ask some people randomly. So Ceren, do you remember the master theorem? Is Ceren still with us? Anybody remembers the master theorem? What should be the format of the recurrence Tn so that we can apply the master theorem? In what cases can we apply the master theorem to quickly find the theta bound of a given Tn, T of n? So nobody remembers it? Okay, yes. So Vladislav and Emir, so T of n must be in the format A times T of n divided by B plus f of n, where A, B are positive constants and f of n is a positive function. Now, if we look at this recurrence, could we apply the master theorem directly? We could not, right? Because it is not in this format. It is not in the format A times T of n divided by B plus f of n. It's not in that format. Which means that we have to resort to our traditional method of solving recurrences, which was constructing a recursion tree. Can you construct a recursion tree for this T of n and try to guess a bound for T of n using your recursion tree? Can anybody do this real quick, like in, I don't know, 30 seconds? Can you try? Can you all try drawing a recursion tree for this recurrence and guessing, finding a guess for an upper bound for T of n using your recursion tree? Okay, let's not wait further. Let's do this together. Remember that for constructing the recursion tree, we need to expand the t terms within a tree. So this is, initially we start with t of n. Okay, we do one more expansion. After the first expansion, now note that this is the definition of our T of n plus some t terms. Since n is already in open form, we write down the expression in open form, which is n, and then as the left child, we will represent this term T of n divided by 10, T of n divided by 10. Represent the second term, which is T of 9n divided by 10. T of 9n divided by 10. Okay. Now, if we look at this small tree consisting of 3 nodes, n is at the root and T of n divided by 10, T of 9n divided by 10, summing up all these 3 terms, we know that should give us T of n, because that's how our T of n is defined. For the next expansion step, we do the same thing to expand further these t terms. We already have n at the root. So n is here. Now, how can we expand this left child, t of n divided by 10? To find out the expansion that we need for this t of n divided by 10, we need to use our formula. Okay, in this formula, which is for t of n, to find out t of n divided by 2, we need to replace n with n divided by 10 everywhere. So t of n divided by 10 will be equal to t of n divided by 10 divided by 10, which is n divided by 100. Okay, and then t of, for this one, 9n divided by 10 divided by 10. So this will be 9n divided by 100 plus n divided by 10. So what we have done is replace n with n divided by 10 everywhere in the equation, which gives us n divided by 10, n divided by 10 plus t of n divided by 100, t of n divided by 100 plus t of 9n divided by 100, t of 9n divided by 100 So if we should be able to see that summing up these three terms, n divided by 10 plus t of n divided by 100 plus t of 9n divided by 100 gives us this t of n divided by 10. So this side is done. Now let's do the same thing for t of 9n divided by 10. How can I represent the tree, the subtree of this term, t of 9n divided by 10? To do that, again, we do the same thing. In the equation for t of n, we will replace n with 9n divided by 10 everywhere. So this will be, the last term will be, the last term in open form will be 9n divided by 10 plus these t terms where we replace n with 9n divided by 10. So this first term will be t of 9n divided by 100, t of 9n divided by 100. What will be the second term? So n will be replaced with 9n divided by 10, which means that this whole thing will be 81n divided by 100. So this will be t of 81n divided by 100. Now, you can imagine that we can continue these expansions further, okay? With these expansions further to have a recursion tree at the end. Now, what we need to find out is what is the sum of all the terms in this tree if we continue our expansions all the way until the end, where we reach the leaf level when we no longer have t of n terms, but t of some constants. So what would be the sum of all the terms in that case? To find that out, we were doing the following in our previous exercises. We were finding out the sum of the terms in each level of the tree. Let's first do that. What is the sum of the terms in the first level? Level 0 sums up to n. This is level 0. Next level, level 1, the sum of the terms is n divided by 10 plus 9n divided by 10, which gives us again n. Now, you can imagine, you should be able to see that the sum of, if we further expand these t terms at the third level, the sum of the terms will again be n, because in here we will be left with n divided by 100, 9n divided by 100, 9n divided by 100, 81n divided by 100. So the sum of the terms in here will also be n, which means that we can guess that the sum of every level in our recursion tree will be n. The only thing we need to find out is then what is the height of this tree, or in other words, what is the number of levels that we have in our recursion tree. Because if we can find out the height, then we can simply multiply the height with n to find out the sum of the terms in this recursion tree. Any guesses regarding the height of this tree? What is the height of the tree? How many levels do we have in this tree? So at level 0 we are expanding T over n. Note that this is an unbalanced tree, but we should be able to see that this right branch is actually longer, has actually a larger height than all the other branches. Okay, so even if we are being generous and we count the longer branch, what is the number of levels in that longer branch? That will give us the height of our tree. In the first level level 0, we are expanding T of n. Let's call the levels with k's. So at level k equals 0, we are expanding T of n. At level k equals 1, we are expanding T of 9n divided by 10. So this is at k equals 1. At level 1, we are expanding T of 9n divided by 10. At k equals 2, so this is k equals 0, k equals 1, this is k equals 2. At level k equals 2, we are expanding T of 9 divided by 10 square times n. So 9 divided by 10 square times n. What does these three tell us? If we continue further, in general, at level k, this means that we will be expanding the following term, T of 9 divided by 10 to the k times n. This will be the term that we are expanding in our tree at level k. Okay? Because for k equals 0, this is simply n, because this is 0, n. At k equals 1, we are expanding 9 divided by 10 times n. At k equals 2, this is 9 divided by 10 squared times n. At level k equals 3, it will be 9 divided by 10 to the power cube times n, and so on. Now, to find out the height of this long branch, we want to find out at what value of k does this long branch reach to a constant t? At what level would we be expanding some constant? So we can make this equal to 1 or 2, any constant we want. With this equation, if we solve k for this equation, that will give us the level k where we are expanding T of some, which represents the leaf level of our tree, which represents, in other words, the height of our tree. Okay. Now, how can we solve for k? In this equation, we have that n is equal to 10 divided by 9 to the k. Now, if we take, with this equation, if we take the logarithm of both sides, we have log n is equal to k times logarithm of 10 divided by 9. Since this is a constant, we can forget about this constant. Then we can see that k is basically log n. So this means that our height, the height of this recursion tree, is log n. And since we have the sum of every level evaluating to n, then we simply multiply log n with n to find out the sum of all the terms in this tree, which basically gives us a bound, a guess for the bound regarding this recurrence. Then we guess that T of n is big O of n times log n. Was this analysis clear for everyone? Was this given this recurrence, can we all see that by constructing the recursion tree and summing up all the terms, we arrive at this upper bound n log n for the given recurrence? Are there any questions on how we have found this bound n log n? Any questions regarding this part? Okay, note where we started with this recurrence. We started with the assumption that, let's say that the partition does a bad partitioning so that it leaves 10% on the one side of the array and 90% on the other side. But with this solution, we see that even if such a bad case arises, the running time of quicksort is n log n. You can even consider further even a worse partitioning so that, let's say, even only 1% is to the left and 99% is to the right. You should be able to see that all this discussion that we have done in here will almost be the same, such that even if we have the recurrence Tn equals T of n divided by 100 plus T of 99n divided by 100 plus n, even if we have such a bad recurrence, the recursion tree method will almost work the same. We will have n as the sum of all the terms and the running time will still be n log n. This should tell us that in general, even if bad input instances are given to the quicksort algorithm such that the partitioning ends up with quite an unbalanced division, even in such cases, the running time of the quicksort algorithm is still n log n, which is the same as the running time of the best case. This should give us an intuition that the average case or the expected running time of the randomized quicksort algorithm should also be n log n. Because even if bad cases arises, the quicksort doesn't have a bad running time, such that its running time is still n log n. To sum up this discussion regarding quicksort, best case theta n log n, worst case running time is n squared, and assuming that we have done that small change where we randomly pick our pivot at the beginning of the partition algorithm, then we can do an average case analysis, and the average case analysis tells us that the running time is still the same as best case, which is n log n. Okay, so with this, now we have finished the analysis of the quicksort algorithm. Any questions in general regarding the quicksort algorithm, its analysis in terms of best case, worst case, and right now we have seen the average case analysis. Any questions about any of these parts? If there are no questions, we will stop here. And in tomorrow's lectures, we will discuss the lower bound, finding a lower bound for the problem of sorting, because so far we have seen the four sorting algorithms: insertion sort, merge sort, heap sort, and quick sort. And we have seen that merge sort and heap sort has the same running time, n log n, no matter what. They don't have any worst case or best case. And quick sort, its best case is n log n, and average case is also n log n. Tomorrow we will see that no algorithm that basically uses the same primitives as these four algorithms, and that primitive is basically doing comparisons and doing swaps on a given sequence. No algorithm that uses the same primitives can do better than n log n running time in terms of solving the problem of sorting. Okay. With that discussion, you will have an idea regarding analyzing problems for lower bounds. Okay. Tomorrow we will do that discussion, but for today we will stop at this point. Okay, thank you. See you tomorrow then.